Hello. So now for a little bit of a break, we're just going to talk about algebraic number theory. If you haven't seen a lot of algebraic number theory, you might want to just take this as a black box, this result. But I wanted to prove it, because if you have seen some algebraic number theory, this is a very nice theorem that puts together basically all the finiteness theorems of Galois of algebraic number theory about number fields in a very neat way. So here is what I want to prove. Here's the following result. Let K be a number field. And let S a set of places, a finite set of places, in fact. That's important. Set of places of K that contains all the infinite places. So it contains all the infinite ones. And let M be bigger or equal to 2 be an integer. Let L over K be the maximal. Sometimes we call this, sometimes we might want to call L to be K as abelian or something, or K as M, abelian, some decorated name that keeps track of all the things that are changing here. But this is the maximal abelian extension of K having exponent M. So the Galois group is abelian and has exponent M, with one more condition, which is unramified outside of S. Okay, so that is saying that we only allow ramification at the primes that we've chosen in S. So if S has no primes, then we're talking about an unramified extension at the finite places. If N has one finite prime, then we're only allowing ramification at this one prime, etc. Okay, the result is that L over K is a finite extension. So what this is saying is that if you start cooking up extensions that are unramified outside S of K, that are abelian, and the exponent is M, then you cannot come up with that many. There's only finitely many such extensions, and you take the compositum of all of them, that gives you a finite extension of K. So here is a sketch of the proof. Sketch, because I'm going to assume a few facts of algebraic number theory. First of all, two assumptions that we're going to allow ourselves. We're going to be able to grow K, and we're able to grow S. And if we prove it for the growth case, then it's also true for the smaller case. So first simplification is that if K prime over K is finite, and the result is true for K prime, then it is true for K. True for K. Why is that? Well, the reason is that, so suppose you have K and a finite extension K prime, then you have L. Let me write L here. If you go to L intersect K prime, and this is too crowded. Let's just go and do a nice diagram here. So K I go up by a k prime extension. I have my L, my maximal abelian extension of k, exponent m, and ramified outside S for k. And then there would be the analogous one for k prime. But if I go up to L intersect k prime and consider L k prime, then it turns out that, well, this L over k is abelian of exponent m. Then L over this intersection is a subgroup, so it is also a subgroup of an abelian group of exponent m, is abelian of exponent m. And if this, the way Galois group works, if this is Galois, abelian of exponent m, this group is actually the same one. So Lk prime is an abelian extension of exponent m of k prime and is therefore contained in L prime. Okay. So the reason why I can extend it is because L is actually contained in Lk prime, which would be contained in L prime, and therefore, if L prime over K prime and K prime over K are finite, then L over K would be finite. Okay. So I can grow my field K if I want to, and I am going to, we are going to grow K to assume that the nth roots of unity are in K. Or replace, if they're not, then replace K by K prime, which is K adjoin the nth roots of unity, which is certainly a finite extension. Okay? This is already not a big, assumption, because in the case of elliptic curves, we've already assumed for the Wigmore-Delvey theorem that the M torsion is contained in K. But remember that the existence of the Weil pairing told us that if the M torsion is defined over K, then the mth roots of unity are defined over K. So this is already happening in our case of interest. Great. So let's do one more reduction, is that I can increase S. So I can also, we may increase S. Because the maximal abelian extension unramified outside S of exponent M is contained in the maximal abelian extension unramified outside S prime exponent M if S is contained in S prime. Why is that? Because we are just allowing more ramification, right? Remember that what we are saying is that the maximal abelian extension unramified outside S, we're only allowing ramification at S. So if we increase S, we're allowing more ramification at other primes. So that is a bigger extension, if anything. Okay. So this is, I can make S, if I want, bigger, because that is going to increase the size of L. So if the larger L is finite, then the other one is finite as well. So this would be what is L for S, while this is L for S prime. So if this larger one is finite, then the smaller one is finite as well. What are we going to do for that? Why do we want this? I'm going to increase S in two ways. I'm going to increase S so that for technical reasons that we will see later, I want a certain ring to be a PID. So RS is a ring of S units. So these are elements of the number field such that the valuation is bigger or equal to 0 for all the places not in S. Okay, so what is that? If I forget about the not in S part, that is the ring of integers. So if S is empty, this is the ring of integers. If I throw things in S, as I'm throwing things in S, what it's happening is that I'm allowing denominators are the primes in S. So if S has one prime, I'm allowing fractions that are divisible by this one prime. Okay, so this is what's called S units. And the ring of integers is in there always, but it may be bigger if I'm allowing some denominators. So I'm going to increase S so that this is a PID. Really, can you do that? A fact from number theory is that, yes, I can do that because the class group is a finite group. Okay, so what am I saying? What I'm saying is that take this ring, RS, and look at it if it's a PID or not. If it's not a PID, then there are classes that are not principal ideals. By the finiteness of the class group is ideals modulo principal ideals. There may be only finitely many of these ideals are going to be only finitely many of these ideals, or the ideals that are non-principal are generated by a finite number of ideals. So I just have to, and those actually have generators that are prime ideals, so I just have to throw in those into the set S, those that were generating ideals that are not principal, throw those primes into S, and therefore now those prime ideals become units, and they don't bother me anymore, and I can make this be a PID. As you see, this is a sketch because I'm waving my hands here. We're going to do that a little bit more technically later, but in any case. And also, so I can do that, and also I want to enlarge S so that the primes that divide M are in S, which was also part of our previous proposition. Okay, so this is going to give me some bigger S. That's fine. I can live with that. All right. So later we will actually just keep track of these items to try to find an actual bound on the rank of an elliptic curve. But for the time being, let's just prove that this L extension is finite. All right. Now, one more thing that I'm going to use is another fact from number theory, which is the following, which is what's called Kummer theory. What Kummer theory tells you for abelian extensions is the following. If the mth roots of unity are contained in your field K, then the maximal abelian extension of K of exponent M must be obtained by adjoining mth roots, delete that, mth roots of elements in K. So so if I have some abelian extension, the maximal abelian extension is, so the maximal, what this is saying is that the maximal, without restriction about ramification, the maximal abelian extension of exponent m is k adjoined mth roots of things in k. That is an abelian extension when the mth roots of unity are in there. So by this, L, which is maximal abelian extension exponent m, but with some control ramification, is the largest subfield of K ABM, as described above, unramified outside S. Okay, so I just need to know which ones of these extensions give it ramification outside of S, right? So when I take an mth root of an element of K, when do I have ramification outside of S? So so now let's look at that. So suppose that K adjoins the mth root of an element A for A in K. I want to know, when is this ramified? Well, that is the extension that you get by taking a root of this polynomial. And if nu is a place and is not in S, so it's a finite place because S contains the infinite places, then also because we've extended S, the valuation of M is 0. And then it turns out, I'm also, I don't know how much you know about proving what things are ramified or not, but it turns out that then this is ramified locally this is unramified if and only if the order at nu of A is 0 modulo M. So essentially, if A is an mth power, then I don't have ramification. And it's an if and only if. Okay, so it's if it's an mth power of in the maximal ideal, okay, at nu and ramified. Great. So so then what this tells me then is that putting Kummer theory together with this fact about ramification is that L is K adjoined mth roots, because of Kummer theory, it has to be of this form. But to be unramified, I have to be careful what A's I pick. And the A's I'm going to pick are in the following set TS. What extension I get is only good up to mth powers. So I can classify this by classes modulo mth powers. Okay, and classes such that I want this to be unramified at nu. So the order modulo m, I'm sorry, this was supposed to be, this is not modulo maximal ideal, this is modulo m being the integer m. This is just this is just a congruence of integers. Okay, so it has to be that the order of A is 0 modulo m for all nu in mk and nu not in S. There you go. Okay, so that is L itself. So to conclude that L is finite, all I have to do now is to prove that there is only this finitely many. TS is actually a finite set. It's a finite subgroup of K cross modulo K cross to the nth power. Okay, so finally we need to prove that TS is finite. Because if TS is finite, then certainly L is finite, because I only have to adjoin a finite number of mth roots of elements of K. So to do that, notice that there is a map from RS cross to TS that sends, what does it send? Well, it sends a unit to its class in K cross modulo K cross to the nth power. Since U is a unit, modulo, it's an S unit. Remember what RS was. RS was units such that the valuation is bigger or equal to 0 for nu not in S. So if I have a unit, certainly the order is 0 itself. It's not mod 0 mod m. The order is 0 at every nu, right? Because it's a unit. So so now what I need to prove is that this map is surjective. That is surjective. So prove that this map is surjective. So let A be in TS, then A RS. So consider the ideal A times RS. The ideal A times RS, everything that is in S is a unit in RS. So I don't care about the things that are in S. What I care is about the valuation of things that are not in S. But the valuation for things not in S is 0 modulo m for everything not in S because of A being in TS. Then ARS is an ideal and it is the mth power of an ideal in RS. Okay, because of this. So this condition tells me that. But since it is the mth power of an ideal in RS, and RS is a PAD, then ARS is generated by an mth power. Okay, so if it is an ideal, we have that ARS is the mth power of an ideal, but B itself is generated by an element because it's a PID, and therefore we have that ARS equals B to the M RS, and therefore there is a unit. There's a unit in RS such that A is U times B to the M, and then U, this unit, maps to A in the under that map. Okay, it's in the same class modulo mth powers as A. Therefore, this map is surjective. Okay, so we have, let's do a recap here, what's happening. Let me just pause there for a second. We've proved that that map is surjective. So again, here's the recap. We had L was the maximal abelian extension and ramified outside as exponent M. And Kummer theory told me that L is contained in K adjoint mth roots of A. And local considerations about where is this going to ramify told me that L is the extension I get from extending by classes in TS, with TS being classes modulo mth powers, such that the order at each nu is 0 modulo m. Okay, so it is in an mth power of the maximal ideal. A is in the mth power of the maximal ideal, and this is for all places not in S. Okay, and what we've just proved is that there is a surjective map from RS cross into TS. Okay, I just need to prove that TS is finite. Moreover, clearly RS cross to the mth power is in the kernel of, I don't know how to call this, let's call that psi. Okay, and therefore I get a surjection modulo mth powers. It surjects onto TS. Great. So now we just need one final big canon to conclude the proof, which is that Dirichlet S unit theorem. You might know the unit theorem that tells you that a number field, the units in the ring of integers of a number field, is what is it? Is a modulo roots of unity, which is a torsion, modulo torsion. It's a free module of rank what, R1 plus R2 minus 1. That is the number of infinite places minus 1. So if you want S units, and to know what is the rank of S units, the Dirichlet unit theorem, let's fix that N, tells you that RS modulo torsion, so modulo roots of unity, is finitely generated, is free of rank. It actually tells you the rank of this module, of this unit group. It's of rank size of S minus 1. Whoa. Here I'm assuming that the infinite places are contained in S, which we are assuming anyways. But for the S unit theorem, it tells you that. This is fantastic, okay? This is a fantastic theorem. This is a fantastic theorem. And this is fantastic because it tells me then that, in particular, RS cross modulo RS cross to the nth power is finite. And therefore, because this surjects onto TS, TS is finite. And therefore, L is finite. And that's what we wanted to prove. Okay. way over time, but that is our intermission of algebraic number theory to prove that this extension of the maximal extension, that is abelian and ramified outside S of exponent m, is a finite extension of K. And therefore, we are going to conclude, because we have just proved in the previous lecture that that the extension L we were interested in was actually contained in this. It was abelian exponent S and exponent m and ramified outside a finite set of places S, and therefore we're going to conclude the Mordell-Weil theorem. So we'll put together the proof next time, and then we're going to sort of like go back into this proof and then just do a summary so we can keep track that we can actually find a bound on the rank of an elliptic curve that depends on the number of places and a few other things. All right, I'll stop here.